We've recently been discussing magnetic circuits, and what makes magnetic circuits go is the ferromagnetic material, just like copper makes an electrical circuit go, right? Using go loosely here. There's a subtle detail that we've been skating around regarding ferromagnetic materials that we should cover now. And the detail is not terribly important to our course. However, it is important to applications, some applications anyway. And so after this course, after school or whatever it is that you're doing, you might find yourself in an application where you need some of the details covered in this video. So let's address that now. It's often the case that mu and b are proportional to one another. So if I had b up here in, let's say, Tesla, and did I say mu and b? I meant h and b are proportional to one another, and we'll say this is amp turns now per meter, right? Because been talking about amp turns, and they're usually proportional, b and h, and that's because of this relationship, right? So if I drew the ordered points b and h on this thing, you'd see a line that would go through the origin, and the slope of that line would be mu. For ferromagnetic materials, say silicon steel, that's not the case. And I just want to take you through it a little bit. Let's say we started with silicon steel and it was completely demagnetized, so we're at the origin. So the Earth was created and now we have some demagnetized silicon steel. If we increased the magnetomotive force H, or essentially H, the amp turns, then what we would see is something like this. It would increase B rapidly up until some point, and then it would start to saturate like that. So clearly that's nonlinear in ferromagnetic materials. And maybe this point of increasing rapidly is 100, and this for silicon steel that might correspond to zero point 0.6 Tesla. And then there's also maybe it starts to saturate, just speaking roughly here or loosely, at 200 amp turns per meter, and that might correspond to 1 Tesla in silicon steel. And we'll call this point where it begins to, or where it's saturated, about there. We'll call that point X. Now, what's really cool though about ferromagnetic materials is that they have memory. And so, if you increase the amp turns, the magnetomotive force, all the way to when you're at point X, and then you started to decrease it again, take it away, essentially taking away the magnetic field, what you see, now I'll make another plot over here. I guess I need all four coordinates, all four quadrants, but I'll just start with this for now. What you see when you decrease from X, so let's say you are here at X right there, and now you decrease the magnetomotive force, you'll go through a curve like this, and you won't actually go through the origin again. So what that means is that if you reduce the magnetomotive force back to 0, B is still non-zero, which is amazing. That means you've permanently magnetized your material. So here's B, maybe BR or something like that. So when you're applying 0 amp turns, you still have magnetic flux density in your material. So this is if you were to start from X now and then decrease, and you'd see a curve like this. Now again, what's interesting here, and maybe you get to this point, maybe call that negative X or something. Now if you increase the magnetomotive force, the amp turns, and go this way, you do not retrace this curve. What you see is a new curve like this. You trace out another curve altogether, and neither one of these is the original path, right? The original path was something like this. Okay, and so this is called hysteresis, or this is the memory of ferromagnetic materials. So this is, it has two states. Either, if you apply if you apply 0 amp turns, you're either at this state or you're at this state down here, and so it remembers, oh, did I come from positive X or did I come from negative X? So that's how ferromagnetic material works, and um, so in this like silicon steel, you might ask, well, what is mu then for silicon steel? Well, it's nonlinear, right, as we said, and so what the way you interpret mu is you look at which point you're at on the curve. Maybe you're at this point. In kind of in analog electronics, we would call that the operating point, but maybe you're here at some specific h and some specific b. Then what you would do is you would use calculus and you'd find the tangent, the slope of the tangent line there, because in that neighborhood, b and h are approximately linear, proportional, and so you look at the slope of the line, and that is what you would call the permeability of silicon steel at that point. But since the slope changes, the permeability changes, and we have a non-linear relationship between B and H. Okay, so that's all I wanted to say regarding ferromagnetic materials. Let's continue on now and let's look at some examples with magnetic circuits. Thank you.